Hello everyone, my name is Hassan Qasim, I'm the technical lead for ML Commons. Today I'm going to present a demo of real-world evaluation of medical AI models on GCP using confidential computing, enabling multiple parties to collaborate without exposing their private assets. ML Commons is a global non-profit organization that develops benchmarks and best practices for AI. It is true that medical AI can transform healthcare, but we need a way to evaluate models on diverse patient data without compromising data privacy. ML Commons MedPerf solves this through federated benchmarking. Models go to the data, not the other way around. Only summarized results are shared, never patient data. However, model IP also needs protection. By integrating with GCP confidential compute, both the data and the model will be securely sent to a trusted execution environment in GCP, and results are securely sent back to medical facilities. GCP makes this easy through its confidential space product. Integrating the MedPerf federated orchestrator with GCP confidential compute can improve global AI studies through scaling global datasets and protect patient data and model IP without data sharing. Now, we will show the integration in action. The demo shows a brain tumor segmentation AI model to be run on a clinical dataset in GCP TEE. There is a benchmark authority at the top. Data owners and model owners will register with the benchmark and then set up their private assets with GCP. And finally, the data owners will run the GCP TEE workload. The benchmark owner creates the base model container that includes the inference script of brain tumor segmentation. This container will be later run in the confidential VM. The benchmark owner then creates the benchmark record, choosing a data preparation container, the inference script container mentioned before, and an evaluation matrix container. The model owner registers the metadata of their proprietary model weights, then links them to the previously defined benchmark. The model owner's storage bucket is currently empty. They will now securely host their model weights with GCP. They will fill in their GCP resources, which are mainly a GCP bucket, a KMS, and a workload identity pool. MedPerf first will check that the cloud resources exist. Then we'll generate a local encryption key, encrypt this key with the KMS, and upload it to the bucket. Then it sets the necessary attribute conditions and mapping on the workload identity pool. Finally, it will encrypt the model weights with the local key and upload them to the bucket. We can see now that the encrypted weights and the encrypted key are in the GCP bucket. Finally, this button will update the IAM policy of the KMS and the bucket. The policy will only allow workloads from the workload identity pool, holding an attested attribute specifying the inference container hash and the model weights hash. We can see, for example, the KMS permissions are now updated. The data owner registers the metadata of their private brain tumor dataset, then prepares the dataset, mark it as ready for inference, and links it to the previously defined benchmark. And now they securely host their dataset with GCP just like the model owner. The encrypted dataset and the encrypted key become on the bucket. The IAM policy of the bucket and the KMS will also be updated. For data owners, the attested attribute of the permitted workloads will also include the data owner's public RSA key for results encryption. For running the inference workload, this is the previously provisioned GCP virtual machine. It's using GCP's confidential space VM image, an H100 NVIDIA GPU, and for now its custom metadata is empty. The data owner will fill their virtual machine information and then invokes the run. MedPerf will first update the virtual machine with necessary metadata. Then it starts the virtual machine. The VM now is starting and the metadata got populated, such as some environment variables, Docker container name, and GPU driver installation flag. Now the VM has started and its serial port outputs are being streamed. For example, we can see that the GPU driver is successfully installed. Behind the scenes, inside the GCP confidential VM, the container will authenticate the VM with workload identity pools of the data and model owners. It will then download and decrypt the dataset and model weights, run inference, and finally encrypt and upload inference results to the data owner's GCP bucket. After some time, the workload is done and the VM is shutting down. We can see the predictions are now written to the data owner's bucket. MedPerf now will download and decrypt the predictions and start metrics calculation. After some time, metrics calculation is done. The data owner can now check the calculated metrics and can submit them to the MedPerf server for benchmark owner to review. And here we are showing in the benchmark dashboard, the benchmark owner can view metrics of finished runs. We would like to thank the following institutions and investigators for participating in this demo by contributing brain tumor data and running the evaluation on GCP and MedPerf. This concludes our presentation. We want to thank our sponsor for making this possible. We also want to emphasize how MedPerf on GCP can improve global AI studies through scaling global datasets, protecting patient data and model IP without data sharing.